that we're putting on at Build Equinox. We're going to be talking about solar design, how to design an economical net zero home. And it looks like we've got quite a few people spread across a few different continents attending. So welcome wherever you are. I don't know whether to say good morning, good afternoon, or good evening to you. But thank you very much for attending, and I hope you find this interesting and that it provides you with some useful information. We're going to go through a couple of things today. We're going to talk about zeros, a solar design, a house design tool that we've developed at Build Equinox over the years. And in addition to that tool, we're going to look at some cases to get a feel for how energy changes as we look at different levels of insulation, different types of windows, different types of heating and cooling systems. And I hope this does two things. First, I hope it, for any of you with an interest in using zeros, it helps kickstart your ability to make use of it. And then second, I hope it starts giving you some reference for where homes are today, as we're seeing them largely constructed in North America, and where they can go right now, not in the near future, but should be doing right now for economic reasons, in addition to those reasons that many of us find important: sustainability, using renewable resources, and so on. So with those two things in mind, we'll get started here. I'm not very adept at using this thing. I'm old school. I feel more comfortable with a chalkboard and a piece of chalk. And so answering questions as well as responding while I'm doing this, I've got a couple people behind the scenes who will answer questions. But anything that I might not answer or am able to get to during the talk, for sure we'll respond to those and we'll post that. In addition, if you need to leave early or at any point in time, my droning and monotonous tone put you to sleep, we're recording this, and that will be online as well as copies of these slides. And so you'll have these to refer to. And some of these I'll go through fairly fast. They're meant to be more background that I just wanted to provide but not spend a lot of time on. And so with that in mind, we'll get started here. I hope everybody's connected on. Check your mute on your computer. We're unmuted here, so as far as I know, everything's a go on our end. I'll be switching over to zeros and show you how to use that. Many of you are already signed up on zeros, and if you're not, that's not a problem for today. It's free to sign up for, and as I'll show you, we're never ever going to sell your information, as well as us make use of it for pounding you with pop-ups and things of that nature. Zeros is purely there to help move things ahead in being able to design sustainable homes. That's the reason why it's built. That's the reason why we've developed it and have made it available. So my name's Ty Newell, and I'll tell you a little bit about us as we get going here. But I'm located in central Illinois, Urbana, Illinois, home of the University of Illinois, and basically in the middle of nowhere. So most likely those of you that don't live around here probably have not had much reason to come through here, but it's a place we call home, and it's some of the best dirt and best land, best sunshine and best rainfall that you find anywhere on the earth. And so that's where we are. As far as Build Equinox, we're involved in a lot of activities. A lot of you know us for our SERV smart ventilation system designed for today's homes to automatically ensure that we're getting fresh air and that it's maintained, and giving us a peace of mind so that we can be off doing other things. But in addition to our manufacturing the SERV smart ventilation system, we're involved in a full range of things, from assessing air quality in homes, which we do through something we call a black box, development of zeros, which we use ourselves for the hundreds and hundreds of home projects we've been involved in now. So it is a tool that we use basically every day, and that I use on campus at the University of Illinois with some classes that I'll appear in engineering and architecture periodically. And then testing, demonstrating, and education. We're at a level where education's essential. Education is the foundation of sustainability. If we don't educate ourselves and upcoming generations, we're going to lose that knowledge that we have and start at ground zero again. So education is essential, along with testing and demonstrating that, in fact, what we're all about is true. Build Equinox, as I mentioned, we manufacture the serve, and we're located in a nice, kind of quiet, rural section just outside of the city border. And we're in a solar-powered building. It's a 4,500 square foot farm building, and if you're reading our newsletter, you'll see data on our building that it is, in fact, a zero-plus building, that over the course of the year, it collects enough solar energy with our 8.5 kilowatt solar PV systems to power everything we do at work. Behind the scenes here are Ben, who's president of Build Equinox, Alex, who's vice president, and myself, the old guy. There we're standing in front of Sunflower, our 2-axis tracker. And if you're exploring our website for the first time, there's a lot of important publications there to take advantage of. The Vermont Serve Report is one of the most detailed reports I'm aware of, and I've been monitoring homes and buildings since the 70s. And this report studies 13 identical homes in Vermont over a couple-year period from the basis of air quality, comfort, as well as energy, and dissects energy into as fine-grained analyses as you'd like. So we find this an important part of both educating ourselves as well as others. How are we wired up? Well, it just comes down to, we want to figure out how we live on a piece of land without spoiling, in the words of Aldo Leopold. And so that's our goal. How do we use technology in order to pass on to future generations a better standard of life than what we've been able to enjoy? Why? I'm fortunate to have wonderful grandchildren. I'm at 5 so far, and these 2 little guys were born in August and September of last year. I just have to look at that. That's what drives me. I'm old. I'm on Medicare, at least now while it is still in existence. And I've been doing this stuff for whatever reason, been wired up to work in renewable energy, sustainable living, resource conservation, my career. In the 70s, as I was in graduate school, you can see a picture of me here, taking a picture in a heliostat mirror at Sandia Labs, a little bit thinner version of my current self. Through when I retired from the University of Illinois as one of the advisors for the 2007 Solar Decathlon. You can see me here and my colleague and accomplice in advising the Solar Decathlon, Professor Michael McCulley, in architecture faculty. Here you can see Ben, who was a member of the team. He was in the MBA program at the university at the time, and one of the few of our team who actually has house building experience from his summer years during high school. And a few other luminaries are in here. Here's Trishan, who went on to Pacific Northwest Laboratory for a number of years. Hiding back here is Luis. I'll talk about him in a little bit. Amy here went on to Bosch Heat Pumps and then is now in grad school at Berkeley. And some of you might find Joe Simon here familiar. He has run the Solar Decathlon for NREL for the last few years. So over my career, since the time I arrived at Illinois to now, it's all been about solar. I developed the Solar Energy Lab at the University of Illinois, and conducted many, many field studies over this several decades. As we look over the decades, today we're going to be concentrating here. Most homes, even if they were built in the 20s or the 50s, have had insulation, some level of ceiling, improved windows added to them. But, you know, there's probably still a few in this range. But this is where we are, and this is about the type of gain as far as the number of kilowatt hours per year. A typical conventional house now with about 6 inches of insulation, the leakage that a lot of contractors are able to achieve now without very significant efforts, about 6 air changes per hour, 50 pascals, to a high performance house in which we are able to seal it to about 0.6 ACH or even lower in some cases. Some more insulation, some improved windows, but maybe not so much improved over what's currently going in homes with Energy Star ratings. And while a significant drop, not that significant as far as your pocketbook, maybe from about $2,000 to $3,000 of utility bills a year to about $1,000 or so. But one of the other things, this red area, this is human loads. This is behavior. This is the things we like to do, like watch TV or use computers or cook. This becomes a dominant portion, and we'll see that in our talk today. Health is much more important than energy. It's much more valuable, both to us personally as well as a society. And if you've been reading our newsletters, you'll see a few that discuss this more directly and the value of it, so we won't labor that point here. But basically, looking here at normalized leakage, if you multiply this by 20, then you have the blower door leakage or the infiltration leakage from blower door tests. So going back to several decades ago, we were maybe at an air change per hour of about 20 with a blower door. We moved to today's homes somewhere between, say, 0.6 and maybe 3 to 6, somewhere in this range. And at the same time, we've seen incidence of asthma increase. And again, this is from a newsletter article in January, so you can find these details in there. If we use that same infiltration data to look at what this means as far as indoor generated particulates, indoor generated pollutants, you'll find that relative to a home back in the early part of last century to today, that we have about 10 times the amount of particulates indoors that we had at that time without smart ventilation. And at the same time, we've increased to nearly 10% asthma. Is one of these the cause of the other? We don't know. Or is it something that exacerbates the other? We don't know, but for sure, these things seem to go hand in hand. We're immersing ourselves in higher and higher concentrations of things indoors, even though we've been able to seal the outdoors. So as we try to put all these things together, thinking of the details of designing a home, the energy, the moisture, the air quality, economics, solar, all of this list of items that we'd like to understand and beyond. What about lighting and water and the waste, the recycling system built in? Where do you begin so that you can then find where do you end? Which way do you go? The 7 steps for this talk is meant to help give a beginning. And in the beginning, what we're going to consider is something fairly conventional looking by today's construction standards, not 1920s or 1890s, but today's. And then taking a progression of steps, sealing the house up, adding what I think is one of the most important developments that's happened over the last couple of decades, heat pump water heater, and now also entering the market, a heat pump clothes dryer, that these two technologies, as we'll discuss later, are essential features of every house and should be incorporated in. They should not be afterthoughts. the couple $100 extra that you would pay for that is going to pay for itself within a very short period of time. But these are very, very valuable technologies. And these are two things that can be done to any home. So as you're thinking of retrofitting, for sure trying to figure out how to seal your house up better, the most important reason is not energy, it's your health. Sealing a house up and then putting in a proper ventilation system is so that you get truly fresh filtered air into your house instead of infiltrated air, which has everything that's stuck in between your walls and the outside. Putting a heat pump water heater, or what's popularly known as a hybrid water heater, is also something you can do. As your water heater gives out, or even if it's not ready to give out, toss it out, whether it's electric or gas, and put in one of these units and seal up that flue vent for your gas water heater, and you've sealed up a big hole in your house. And then moving on to, if we do have the option of adding insulation, how much? What's optimal? And our view of optimal is what's economical. If you do not design a house for economic reasons, you're going to be wasting a lot of money, and that's money you could use, that's less work that you have to put in order to pay for that wasted amount of dollars. And so it's essential that we design economically optimal homes. And then finally, let's see what happens when we power a house with solar. Too many people I hear just keep building solar-ready homes and keep saying solar's too expensive without looking at the overall cost. And Zeros is a tool that will more conveniently let you see what this means as far as your upfront costs, as well as what your monthly costs will be. And then finally, we're putting up solar collectors. What happens if we buy an electric vehicle? I mean, the prices are coming down now. It's like flat screen TVs, where flat screen TVs used to be a few $1,000 TV, and now they're a fraction of the price of today's TV. And electric vehicles are exactly the same. We've got the development and the lower manufacturing volume costs that are causing them to be sold with a premium, but it's a much, much simpler car than the internal combustion engine. And so we're going to see that these cars will take over, and they're going to take over for economic reasons, as well as giving us the environmental benefit. But purely economical reasons are going to move them in as people get educated and understand that power. And one of the things we like to encourage is form and function. You can have it all. We see too many projects in which form is the overriding factor, and people are not looking at how they run the utilities throughout a house, how they run the ductwork. It's left as an afterthought. And then we're hearing that, oh, we don't have enough room for that, or can't you fit this in a 6-inch cubicle space? Put the function into the design at the beginning and then get the form you want. They don't have to be exclusive. You can get both. We're big fans of, my wife and I, of Frank Lloyd Wright, not of his personality, but of his design, conceptual design. And so what we call Equinox House, our house, a zero-plus home that also powers 2 electric cars that are in the garage, that this is what we call a modern Usonian. But as far as form, it could look like any of the homes across the street. Whether you like it or not, some people might call it a chicken coop, others hopefully kind of a sleek-looking Porsche of a house. But regardless of your viewpoint, that's the problem with form and fashion. It's everybody's taste. I would like to say that while I was providing the function side of things, our architect, the wonderful architect, Jean Ascoli, she's a Taliesin Associate Architect. They're hard to find these days. And so, so with what we call our modern Usonian home, she was the person responsible for making our hopes into reality as a modern-looking version of Wright's vision. This dumpster down at the bottom, just kind of, why can't dumpsters look like that? That looks pretty cool. And if you're near Florida Southern College, and if you're a Frank Lloyd Wright fan, you'll get your fill of is designed, it's a wonderful campus to visit. Just also merging form and function. Equinox house hidden behind its simple shed roofs, clear story windows. These are all secondary effects. It's not going to show up significantly in zeros, and it doesn't need to be. We don't have to rely on wishing and guessing and hoping that some of these types of features will kick in and all add up together. But we did put these things in, such as this, what we call the Equinox overhang, that takes low altitude winter sun rays and concentrates them into our clear story windows off this 212 pitch roof and this uplifted Equinox overhang. And then summer sun, relative to this 212 pitch roof, it's reflected back out into space as well as not allowed to go into the house. We shade from equinox to equinox, spring to fall, and you can see the shading for both of these south-facing windows. And this Styrex japonicus tree, if you're reading our newsletter, we had a recent article about it. It just bloomed, and there's a lot of other features about that as to why we planted it. We purposely designed Equinox house 10% window to floor area, about 200 square feet of windows to 2,100 square feet of floor. We'll see why that's true in this talk. We harvest rainwater. We have a 1,700-gallon cistern. We're the first home in Illinois within a municipality to be approved for rainwater harvesting, and we're approved for using that for toilets. But the system is designed for supplying close to 100% of our water needs throughout the year. But just like solar, rainwater harvesting is something folks should become more familiar with. We get a nice, almost 10% bump of solar reflection from spring to fall equinox off of this roof onto our ground-mounted solar collectors. And the only reason the collectors are mounted on the ground is we have a berm that makes it convenient for people who are visiting our home to kick the tires and see a solar collector up close and personal. And then a rain garden in this area that takes overflow from the cistern and is a feature that helps not overload storm sewer systems within urban areas. What I'm going to be telling you about as far as features in a home is not new. Since the mid-70s, in our case at the University of Illinois, the Locale House, that was the beginning of the super insulation movement. Parallel to that was the passive solar movement, and passive solar movement has kind of revived itself again with us finding too many homes with too many windows and then bearing the expense of that. But we'll talk about that more. But basically, the house that we're going to consider in this talk might look like Equinox house. It might look like this nice simple ranch. It's basically a 2,000 square foot home. You might think of it as a 40 by 50 foot floor plan. Here's actually a Locale house. In reality, this was built about 40 years ago by my colleague from the Solar Decathlon, Professor Michael McCulley. This is in Urbana, and I stopped by one day and caught one of the homeowners. This is actually a duplex. I caught one of the homeowners and was just chatting with him and asked if I could take a picture of his house, which he was looking at me a little strange, but I'm used to that. And he said the house is just wonderful, that it really has worked over the years that they've lived in it, and they just love the low energy bills since they moved into the house about 10 years ago. Now, why would we in those 7 steps look at a house without windows? Who builds a house without windows? Well, there's one person. This was in Raleigh, North Carolina. And is that house marketable? Is it economical? I guess if you can find one other person that's interested in a house without windows, but aesthetics are important. People want to buy something that looks good relative to their sense of design and aesthetics. The reason why we're looking at a house without windows in these 7 steps is that in engineering we like to look at limits. What if we put no windows, and then what if we put a lot of windows? And then knowing that most likely the answer for anything in between should have economics that are in the middle of those two limits, should have energy performance in between those limits. And so these limits kind of give us our bearings as far as how far is too far. And again, I'll mention that looks are not important. This house across the street, it's the same floor plan as our house. And in fact, we took the floor plan for Equinox House from another home in our development where we had been doing some field studies for the developer on about 7 or 8 homes. And we liked the floor plan layout, just a pretty traditional ranch home. And then we just put a different looking shell on it. And that's really the only difference between these two homes, except ours is better sealed. It's more appropriately sited as far as windows, and a little bit different level of insulation in it. As I mentioned on electric vehicles, you know, we can economically move off oil now. And the statue in Rotterdam, I think, is just a fantastic statue, just illustrating all the pain and suffering that we're seeing today and have seen for many years due to oil. A lot of folks think that electric cars are only going to be cute little cars for around town, but that ain't true, and more people are realizing that as Tesla and others with superchargers are getting established across the country. 5 years ago, Deb and I drove across the country. As soon as I was able to buy a Ford Focus, I was born in Detroit, so I'm a Detroit kind of guy. As soon as I could buy a car that was built in the Motor City, I did. Unfortunately, you could only get them in New York or California, so we bought ours on Long Island and then picked it up and then drove all the way back, drove up through Canada and down to Detroit. We were recreating a historic 1901 journey that an Oldsmobile made from Detroit to the New York Auto Show. And at that time, gasoline cars were thought the same way, that you're just going to use them around town. And Roy Chapin, a young fellow that worked with Oldsmobile at the time, proved that wrong and just made headlines around the world. And while Deb and I didn't make headlines around the world, we just had a fun trip, made it back home, and we've been enjoying that car ever since. And it's been solar powered its entire life. We've produced more excess energy over the course of the time since we built Equinox House in 2010 to pay for the electric that we use along this journey. Interestingly, Henry Ford's wife didn't like cranking a car and didn't like the noise and smell of gas cars, so she drove an Edison electric car. Now here's the big deal. Solar-powered electricity used for transportation, it requires about 2 to 3 cents per mile at today's costs, and it's getting less and less. Gasoline for a 30-mile-per-gallon car at today's gasoline prices, and who knows where they'll be tomorrow, about 10 to 12 cents a mile. This 10-cent per mile difference is huge. It's saying that as soon as you can get one of these cars to do that, and you'll stabilize your transportation costs. At this time, you're near transportation costs, but cross-country is just getting easier and easier. Just give you a little bit of a viewpoint. Our 8-kilowatt solar array for Equinox House, roughly this much of it, a couple hundred square feet, is what gives us 8,000 miles of driving a year. So not that much is needed, really about the size of a garage roof over the car. That's all you're talking, and overall about 600 to 700 square feet of solar array in our area to get 8 kilowatts. Now zeros. If you haven't gone to zeros, you can do this at any time. Go to buildequinox/zeros. It's nothing we advertise, but we've got users all over the country, all over North America, but beyond using it. You click on subscribe, and then that will let you register and get a subscription key. And we're not going to bother you. Your data is not going to be sold. We're not going to be bugging you. This is purely, we want to see more solar-powered homes built, and to be as an aid for those of you who are involved in the designing process. You can download a PDF that has a description of a lot of the things we'll be talking about here, and a CSV file that has data files that you can import into Zeros to use, and these have the 7 steps that we'll be looking at. The purpose of Zeros is to take the complexity of all of these considerations and put them into one package. And there's additional things we hope to be adding in the future, but as this is a non-revenue generating activity, we don't have the luxury of continuously working on it. But for sure, that is our plan, to keep developing it, putting in better models for like geothermal loops in the ground, rainwater harvesting, and other technologies as we move through toward more and more sustainable living. I won't belabor validation. You can read through this in more detail later, but Luis Martinez, who I pointed out was kind of hiding in that picture in the solar decathlon, he's a professor in El Salvador now and doing great things there. But he was my last PhD student, and the computational model built into Zeros was part of his dissertation, and it's well vetted using what's called best test on a computational platform against things like DO2 and BLAST, which are now merged together in what probably more of you are familiar with, called Energy Plus or E+. And then another validation, looking at it versus experimental data. When we first built Equinox House, it was electrically heated for 1 year, so I could take data over that year and compare it to Zeros. And the solid square points, blue points, show what Zeros predicts for an average year, and then the open are the real year. This kind of loop-to-loop is kind of a beneficial thermal storage of our uninsulated slab floor. We kind of have low cooling costs as we go into the summer, since we have the benefit of ground coupling, and then low heating costs as we start going into the winter. The second year, we had a mini-split, low temperature mini-split heat pump installed. And here you can see how Zeros with typical COP for a mini-split heat pump compares with the data that year. And 2 of these data points, because my wife has an immense family that I guess we enjoy having visit, but there's about a week of November and December with immense amounts of cooking and people activity. And if I subtracted the Thanksgiving week and the Christmas New Year's week out of that, that data actually looks like this. And so other things happen. And if we had, say, an even higher efficiency coefficient of performance of about 4, rather than about 2 as I use for the mini-split heat pump, something like a geothermal or today's generation of mini-split heat pumps, that would be the kind of energy gain, kilowatt hours per day, we would expect versus outdoor air temperature. Further validation, check out this report that we wrote on the SERV and 13 identical homes. There's 13 homes in this data here over a couple-year period. And while Zeros would say, and it comes right through the average of this home energy, so again, kilowatt hours per day versus outdoor temperature, and these are daily data points, so you just see the variation of lots of people at home, no one at home, cloudy days, sunny days, all sorts of things going on in real life. And this is why you want to be prepared to do more than just the average conditions. But with 1 person in the house versus 3 people in the house, and these homes had, on average, close to 3 people per home, these 13 homes. And then these are 5 conventional homes that we've collected data. These are monthly averages. But you can see how conventional construction compares to the kind of construction like Equinox House, and then these Vermont homes, and then many of the homes that you're involved in building. So Zeros is well vetted, and we're going to use Zeros directly rather than go through and show you these. Again, these slides are available to help prompt you, but really it's a learn by doing type thing. How to import or export the PDF files, what the files look like when you're in the projects, and then what the overview page, probably the most important page in Zeros. Once we maneuver our way through these 7 steps in Zeros, then we're going to come back and look at a summary of the 7 steps and what that means as far as performance. So for example, case 1, just a conventional house with 3 occupants, we'd assume that, predict that to have maybe 13,000 kilowatt hours of energy usage a year. If we add 500 square feet of windows to the south facade and remove 500 square feet of insulated wall, we would see an energy drop in our area because of that. Other areas you wouldn't. If instead of adding windows, if we seal the house up and then put in a smart ventilator that gives us the fresh air we need to keep people healthy, we would see a much bigger drop in energy relative to the addition of windows. Once we would seal it up and ensure that we have fresh air, if we put in a heat pump water heater, we see another large jump in energy by the addition of this new technology. And then finally, as we optimally insulate this house, we'll be doing the house without windows, we'll end up here with about 8,000 kilowatt hours, which actually is about what we're using in Equinox house. Now these other cases are the various cases where we start adding solar and looking at the different costs. So once we've satisfied this amount of energy, solar meets that. And then over here, we're looking at the solar needed to just supply the house. And these 2 cases that we'll discuss, this is today's solar installation costs in our region. And this was just a few years ago. As we bring in the economics, we'll see the powerful impact that this has had on decisions that we should be making now. And then if we add about 3,000 watts or 3,000 kilowatt hours more of solar to the house, that would give us about 12,000 miles of electric vehicle driving. Our energy production for the house would now exceed what we need, and that could go into transportation, and we'll see the very significant impact that has. So we'll move through those, but let's move on to exploring Zeros a bit, and I'll see if my Zero screen is still active. So when you sign into Zeros, it will take you to, I think, to this initial envelope screen. And there's not a lot going on here. You should explore it and just see what's in here. For example, this projects screen shows the different files that I have. Right now I just have kind of a base case file that you'll get with Zeros. Plus, if you import the CSV file, it will add a project. And with the project, it will load these different cases. The conventional with all south, no south wall, but all windows on the south, and then sealing it, and then a heat pump water heater, optimal insulation, and then adding solar. So I have case 1 up here, and if I go over to envelope, just to get your bearings, we're going to look at 3 people. People are very significant, and we'll see how that impacts energy and economics. 2,000 square foot home, and yeah, I fudged these a little bit, but roughly a 2,000 square foot ranch would have about 2,000 square feet of wall area. It might be about 10 feet tall or so, with thinking of a 40 by 50 floor area. And a roof of 2,000 square feet, a building volume of about 20 cubic feet. And we're starting with the conventional house having about a blower door of 7 air changes per hour. With that amount of leakage, with 3 people, as we'll see, that's on average enough to keep the air reasonably fresh. But from our field studies on air quality in so-called leaky homes, where the air leaks and where you live are 2 different things. And so typically this is not a healthy home. And And so having purposeful ventilation is still important, even in these leaky homes. Foundation area, and then a very simple ground loss model. There's a series of ASHRAE journal papers that Ben and I wrote a couple of years ago, 12-article series over the course of a year. If you read the article, maybe from like November or so of that series, we wrote a paper on ground loss. And while this may seem way too simple of a model, it's not. It gives you the information you need to know how significant ground loss is. If you're going to put some insulation under a house, maybe you have about 1 watt per square yard, or half a watt. If you want to look at the ideal insulation, perfectly insulated, you can. Roughly without insulation in the ground, but definitely insulating the foundation area, that you'd have, say, a loss of about 2 watts per square yard. Our conventional house has 6 inches of wall insulation assumed, 12 inches of roof, and looking at the windows, this first case, no window area. Keeping in line with simplicity, but at the same time not giving up accuracy. And this is very important to realize, that we are very, very accurate and all the detailed computations are made. We're just trying to make life easy for you. If you want, you can put in detailed U values for windows and detailed solar heat gain coefficients. But if you simply want to designate it as a super window, which would be typical of today's high performance windows that many of you are familiar with, or an Energy Star, or if you want to see what it looks like relative to single glazed, or what would be, say, a storm window on a window of decades ago, you can do that. And this is more than enough refinement as far as those energy factors on a home. And then the same over here on solar heat gain coefficient. As we have written over here, high means about half of the solar energy incident on that window makes it through, and a low solar heat gain coefficient, which those of you in the south should be always considering, about 0.23. And then basically for any of these orientations. And then the overhang is just a simple model, yes or no, but basically it says from equinox to equinox, which for most places throughout North America, that's about the time when you want to cover and then uncover windows from spring to fall. It just gives you kind of an estimate then of what a good overhang might do in your case. Going on to systems, again, keeping it simple. Yes, these things are temperature dependent, like the heating seasonal performance factor for a heat pump and cooling systems here. And these are good, reasonable values for those. Daily hot water usage, this is average for the US as far as hot water per person. You have a teenager, that might be 50 gallons per day. If you are someone who wants to save hot water and don't shower, that could be 0. And then as far as heater performance, the worst you can do is a coefficient of performance of 1. That's an electric water heater. A value of 2 to 3 is typical of today's hybrid water heaters, and we'll explore that. As far as the energy usage in a house, 200 watts as a base, the energy that a house would use just from things going on that aren't so per person dependent, and then add maybe another 50 watts per person, but again, you can change these. And for this conventional house, these are purposely kept as low values. These might be more like 400 watts for, say, today's conventional house with 100 watts per person. Figuring somebody has incandescent lights in various areas, not such efficient appliances, and then other excess energy usage. But if you look at the Vermont study, this is in line with what we see on it for base energy. Also on systems energy, the ventilation system. A lot of you who are familiar with various ventilation models will find that now in our base case, it's leaky enough that we're assuming no ventilation. but that there's ERVs and HRVs. But a lot of these models just simply model the HRV and don't properly, if they do have an ERV capability, don't properly model ERV, which can also transfer moisture between streams. So in zeros, you can model an HRV. You can model an ERV. In the case of the ERV, you're going to have your latent recovery. 0.6 to 0.8 might be typical for a number of these systems, and then 0.6 to 0.9 maybe on the heat recovery side, and then whatever ventilation rate, and then whatever fan power for operating at that. So that lets you explore that. And then as far as smart ventilation with something like our SERV system, you're just going to tell it, here's the air quality I want. I don't want it to get above 1,000 parts per million. I don't want it to get above 900 parts per million. So you can check that out. And if you look at my site, if you look at Equinox House, which has live data online, you'll find that I keep my house at 900, but on average what that means is that we're typically at 600 to 700 parts per million in our house, the level that we prefer. Under comfort, this is a unique feature too that you typically don't find in other models. Now we're just setting it all at 72 degrees throughout the year, but you want May to be 80 degrees in there, set it at 80. And if it needs heating or cooling to be at that, that's fine. You can adjust those until you see that there's no heating or cooling needed. So you can see what happens when a house floats. This is the ambient temperature plotted relative to what's being chosen. And then another unique feature is setting the humidity. Because we have accurate moisture models within zeros, and these have been checked versus the moisture that we collect in Equinox House over a several year period. And the two are in very, very good agreement that you set the humidity, and typically we don't go much below 20, just figuring 20% humidity in the winter, just figuring that's getting too dry to where dry skin and nosebleeds and things like that start becoming irritants, and then generally not above 60% humidity. But again, you're free to ramp it up or ramp it down in humidity and then see the energy impacts of doing that. Now we get to the overview, and this is where the important stuff happens. This is where we see a summary of the costs. Here's the capital cost for building the house. And so this basic conventional house that we're looking at has a cost of about $214,000 with a base cost that's been assigned of $200,000, and then the things relative to comfort and energy, the utility bill, the insulation costs, the heating cooling system, the water heater. So this is a basic electric water heater. And then a life cycle cost based on 100-year of operation. So things like windows that might get replaced every 20 or 30 years, or a heating or cooling system. Those repair costs, you can see the heating system over 100 years gets replaced, I think maybe on a every 20-year basis, and the same for the cooling system, and the same for the water heater, I think maybe 15 years on that. And overall, the life cycle costs. And somebody doing economics will want to know what gives me the lowest lifetime cost, and that's what this number is. So the goal is to drive that down to being as low as possible. These sensitivity arrows are telling us if any of these quantities are increased, whether that's good or bad. So for example, if I increase wall thickness, this green is saying, yeah, that's good. On the life cycle cost, it will go down if I increase wall thickness, and energy will go down. These two things don't always agree. For example, on windows, this is telling me in this climate for this house, I will see energy drop when I add a south window. But because of the cost of the window, I will see the life cycle costs go up. So you have to decide, is it more important to you to save energy even though you're wasting dollars or not? You decide that. Other windows, typically on north, east, and west sides, unless you're in South America, they're going to be inefficient from an energy viewpoint as well as a cost. And with the solar costs I have built in, this is saying, hey, don't wait for solar, put it in now. And then these other things. If I use more hot water, it's kind of common sense. Cost and energy is going up. The base electric and occupants. So we have this direction to help us optimize rather than letting some automatic optimizer like in a BOP type simulation from DOE just take over. We want to keep the human involved as you move through these pathways in design. And then over here, what you might get from Manual J as far as capacity needs. We predict design day. These are a little different than ASHRAE, but they're based on that data. We add a little bit of high and low temperatures to the design day for heating and cooling, and but not extreme. And if you look at detailed weather data, as we've done for these locations, basically these are temperatures that are well within the extremes that these locations see. For example, here in Illinois, since we're looking at Urbana with this data, that we've seen -20 in this area, and we've gotten up to 110. And so these are well within the extremes. With the design day data, we tell you then, well, since this house doesn't have any windows, it doesn't know if it's sunny or cloudy outside. And it would need about 6 kilowatts of heating capacity for the design day conditions. And this is about a 2-ton system, about 20,000 BTUs per hour. So that's not that bad. On the cooling side, again, because sunny and cloudy doesn't matter, this house doesn't need a very big air conditioning system. A little bit less than 1 ton, about 8,000 BTUs per hour. And then over on the latent side, this house, based on its infiltration, and then the human moisture load is also part of this. It's saying that this house during the winter, with the humidity levels we've chosen, really doesn't have any humidification needed. Very little energy impact as far as humidifying or vaporizing water. And at most, under design day conditions, in order to keep it about that 20% humidity during the winter, this would be about 7 liters a day that you might add. And things like showering and cooking and plants and other things that are moisturizing the house might do that on its own rather than needing to actively humidify. In our weather, we're very humid in the summer. We get a lot of Gulf moisture coming up from Louisiana and Texas. And so we need almost 30 liters per day of dehumidification capacity in order to keep below 60% humidity during our June, July, and August time period. And so this is telling us the latent that would get added into the sensible side. Now over here in air quality, this leaky house, if that air was nicely distributed to all the occupants, but I can guarantee you that it is not, that 100% of the air coming in as infiltration air is not good. Where it came from, nobody knows. What it's laden with as it enters your house, nobody knows. There's no fresh air purposely being brought in that's just on the other side of that wall. Now it does keep carbon dioxide at a reasonable level, less than 1,000 parts per million, and in a range that's not so bad. And the amount of people that would be dissatisfied with this level of air would be somewhere in the range of 14–15%. This is out of some of the olfactory models that have been produced from the Danish Technical University over the years. On the energy summary, what most people are most interested in. Since this has no ventilation, there's no ventilation energy, but heating-wise, there's quite a bit of a heating load. This is about $500 worth of energy, electrical energy. We have minimal amount needed for air conditioning, and as we'll see in the next case study, that's because of no windows. Dehumidification is a pretty big expense. Again, this is maybe $90 worth of energy costs over the course of a year, but it is one of the bigger energy amounts, and humidification is negligible. Finally, take a look at water heating for 3 people. about 1,000 kilowatt hours per year per person for water heating. That's equivalent to, in this home, what heating energy would be. And then the other loads, 200 watts base load plus 50 watts per person, about 350 watts on average throughout the year. The sum of these two, humans dominate this house, not climate. And that's typical of homes throughout most of North America. So those are some of the details of what you'll see. And up here, I won't go through much detail. I'll let you poke around on that. But you can see what the thermal load is made of as far as wall, roof, windows for each month of the year. And the latent. So on the latent side, you can see that during January, for example, here's how much is coming in, the effective moisture load from the outside. Here's the moisture in an energy quantity as far as the human load. So you take the water that's coming off of people going into the air, and it turns out in January for our area, these are just about balanced. Now as we go toward the summer, and the human load is constant through the year, these variations are just whether it's got 30, 31 days or 28 days a month. You'll see that over here, June, July, and August, we have a net gain of moisture plus what the humans put in. And now we're seeing so many liters per day we have to pull out. And we assume somewhere in the range of about 2 liters per kilowatt hour as a dehumidification efficiency, what the energy impact is on the home. And then all of that boils down into the electric. In order to take all the thermal loads, and with the heat pump that we have assumed for this, with a seasonal performance factor of 10, these are what the heating loads look like. Here's what the cooling loads look like, and they're minimal in this case, and the dehumidification loads, and all these add up to what we have as a net electric load for each month of the year. Now, as we're going to go over the hour, those of you that need to leave, again, this is recorded, so you can pick up the rest of this as we keep exploring. And for those of you that can hang on or still alive with my droning on, we'll keep moving through a number of these, through these cases. Going down to solar, we're not at the solar cases, so we have 0 wattage of solar system PV, but we have costs and other parameters that are put in. And then this economics page is very important. This is where those costs that are in the life cycle costs come in. And on this page, for example, this 2,000 square foot home in our area, we would have a base cost of about $100 per square foot. So I put in $200,000. Some of you that live in nice mountainous areas or coastal areas, maybe this is $500,000, or maybe it's much, much more than that. The lifetime that you want to explore, the cost of the materials that impact energy and comfort. So roof insulation is typically easier to install if you're blowing in some kind of chopped fiber versus wall insulation that has to have some kind of support, and so it might be a bit higher dollar per cubic foot. $5 per cubic foot is typical of like styrofoam. $2, $1 to $2 per cubic foot, typical of blowing in chopped cellulose or fiberglass. Window costs, we see window costs from $30 to $100 a square foot, and a window lifetime, so you can have the replacement costs. Heater costs, these are maybe a bit low, $750 per kilowatt, but again, you're in control of any of these costs and replacement lifetime for these. If it's a heat pump that has both heating and cooling, I just kind of split that cost between the two. But again, you're in charge of those assumptions and have flexibility in that. For the water heater, it's an electric water heater, which costs about $400. The plumbing that goes with that is assumed to be up in the house costs, along with maybe the cost of ductwork and things like that. and whatever lifetime, and then a ventilation system. So if you have something like a serve, this would be maybe a $5,000 item with maybe a 15 to 25-year lifetime, similar to what you'd expect for, say, your heating and cooling system. And then the utility cost. We're assuming 13 cents per kilowatt hour, similar to what we see around here in much of the country. If we overproduce, any excess produced is a donation to the utility here, but if you do have a feed-in tariff that lets you overproduce, or in the case of the electric car, we'll add a value here, and that's a very important value to be able to take advantage of. And then a monthly fee. Our utility charges us about 20 bucks a month, and so even though I'm net zero or zero plus, I do pay a customer service fee. There's some mini windows here that give you a little more detail than the overview page. And as far as these optimization arrows, this is where you can kind of get an idea how significant some of the changes are. So as I mentioned, an increase of any of these parameters shows up as, if it's green, that this is going to be a beneficial decrease of life cycle cost. And on the energy arrow, if that's green, a beneficial drop of energy. So if I add 1 inch of insulation thickness with those costs and R value I assumed, I would drop the life cycle cost over 100 years by about 3,000 bucks. That's pretty good. And I'm going to see a drop in energy. So it's saying I'm not at optimal insulation levels. Let's make the wall thickness more. And the roof insulation, we have 12 inches assumed, so it's already pretty thick. So we're starting to see reduced gains in life cycle costs for each additional inch there. But we do see an added energy as well as dollar gain. So it makes sense to do that. But if I add 10 square feet of north window, I'm going to see a couple thousand gain in life cycle costs. And I'm going to see an increase in energy. South windows are always interesting, depending on where you're located. I'm going to pay about 1,200 bucks over a 100-year lifetime in order to get 50 kilowatt hour per year savings. This is about 5 bucks per year, but it's going to cost me 1,200 bucks over its lifetime. It's just not going to pay for itself. But if that's where I have a view, as we tell people, use windows for light and delight, go for it. We like windows. Our eyes like windows. And so on all the way down through here. Solar is saying, yeah, do this. You're going to save money, and it's going to reduce energy. And look at hot water. If we drop water usage by a gallon per day, or if we increase by a gallon per day, this has as big of a dollar impact on the life cycle cost as an inch of insulation. But this is much easier. Just use less water. And so, you know, we don't want to neglect these people things. As we said, the people are significant in these homes, and even this conventional home. And the base electric, if I can drop 50 watts of energy usage over 100 years, something that might be as simple as turning off some lights or adding some timers or just getting on the kids to turn the damn thing off, this would be much more significant than an inch of insulation. And then finally, you know, speaking of kids, you know, there's 3 people in this house. Once they get old enough, get them out of the house. You're going to save a lot more money over the course of a lifetime. Of course, they're going to be using energy wherever they are, and hopefully they carry on that idea with them. Finally, on finance, how much do you want to put down? The length of your mortgage. So it's fine that we know the economics over 100 years, and we want that as a metric for whether or not dollars are being spent wisely. But now we've got to pay a monthly bill, and I don't want it to be too high. The bank's not going to loan me money if it's above a certain percentage of what I earn. And so this allows you to get a view of how property taxes, insurance rates, and these are typical numbers that we see around us, but again, you can adjust any of them. And then down here are some more details as far as your monthly costs. So this base case, about $1,532 per month. About half of that mortgage. We've got pretty good high taxes around here. Bit for insurance, and then utility costs. And so overall, this is what makes up my living expense for this area. So let's go back here and go back to the summary. We've got about 12,000 kilowatt hours a year for this case one without windows. Let's change this to 1,500 square feet. And I can either use the bar to move that. So I've reduced the wall area of the house. I haven't added windows yet, but let's go down here and calculate this. Now, I calculate that and I see, all right, I dropped about 400 kilowatt hours just by losing a wall. Of course, is that practical? If you think of an apartment as a house that only has one or two outside walls, you know, that's basically what an apartment is. So you can model apartments with zeros. My life cycle cost dropped, my energy dropped. That's kind of nice. But now I'm going to put some windows back in. That 500 square feet of wall on the south side, I'm going to put 500 square feet of windows in. I go to the overview and I'll calculate that. And I dropped another couple hundred kilowatt hours. I didn't drop as much as what getting rid of that wall did. I didn't have to have something in that space. But I see another energy drop. But now we go over to the life cycle costs. I went from about $412,000 to $495,000. And over here, this is telling me, you know, I'm beyond where window area would be an energy benefit. And I'm at about 25% window to floor area ratio, and generally somewhere in the range of about 10% window to floor area is a good place to be, where it doesn't drive your economics, it doesn't drive your conditioning system. Let's look over here at the conditioning system, speaking of that. On the design day, the coldest day of winter, when it's sunny, I would need about 19,000 BTUs per hour, and in our case one without any windows, we had about 20,000 BTUs per hour. So if we had an average sunny day, the heating load would drop by, say, about 5%. But on a cloudy day or at night, and windows detract from thermal mass. They make your house, when it's excessively windowed, drop like a rock in temperature when it's not sunny out. We see that we go up significantly from about 5.9 kilowatts to about 8.5 kilowatts of heating. Similarly, on the cooling side, because we also have the detriment of a sunny day in the summer directly adding air conditioning load, we go from where we were at about 2.5 kilowatts of cooling, less than a ton, to where now we have a need for 2.5 tons of air conditioning capacity. Our latent load hasn't changed, but now we need a much bigger system to keep this house cool than what we did without windows. We look at the finance side of things, where we were at about $1,500 per month. We're now at about $1,700, and a lot of that is because the mortgage has gone up. Because the cost of windows, we go back to the overview, we now have about $22,000, $23,000 worth of windows for that 500 square foot wall area. And over the course of 100 years with replacement of windows, about $75,000 added. We go down to the heating and cooling systems, and that's reflected in a higher cost for the heating and cooling system based on the design day levels as well. And so all that's captured in zeros for your life cycle costs as well as your capital costs that your mortgage will be based on. Now, we move, so case two is just what we changed as far as the south windows. So as you explore these later, you'll see that. Let's move on. I'll go back to case one. Well, actually, I'll just go to case three. Case three is just case 1, except that it has, it will let me, I might have delayed too long in there. So case 3 is, see if I can calculate this and get it to respond more quickly. And if it doesn't, then there's always the have it reboot. So I'll reboot and go back in. I think because I've got a couple of things running there. We'll sign back in, and things should come back in line here. I'm just going to go to case 3, and in case 3, we're back to 2,000 square feet of walled area, no windows, and now up here in case 3, we've dropped the infiltration from 7 down to 0.6, so something equivalent to like passive house certification. No changes in wall insulation, no changes in the economics, the windows, no changes in the system energy. With those changes, we're now at about 10,600 kilowatt hours of energy needed. A little bit of change here in the heating and cooling. Again, without any windows, a sunny day and a cloudy day are the same. And then over here on life cycle costs, we see some drop from our previous. Now, when we sealed it, a ventilation system's been added, and the cost that under the economics I have in this model is $4,500. So about $4,500 added to add some type of ventilation system. And so that cost is reflected along with its replacement cost. And so that's an added cost that we didn't have before as we sealed it up. If we go over here, we see that the air quality is kept below 900 parts per million on average, and similar to the other, 14 to 15% would be dissatisfied. As we look at the finance of this, we see that sealing up the house and adding the ventilator, our mortgage went up a little bit. Our monthly payments are about the same. We're about $1,532. And now if we want to look at what would be case 4, in which we're going to add a heat pump water heater, instead of going to case 4, I'll just simply move this up to a reasonable coefficient of performance, although we're seeing on the market COPs or coefficient of performances of 3 units of heat for every unit of electricity we put in. And if we go over here and calculate that, we see this other substantial drop in energy. We see a drop here in life cycle costs. But over in economics, this water heater is going to cost you more than a basic electric water heater. And I think I had maybe about $800 about what we're seeing here. But you might see $800 to $1,000 for a heat pump water heater. Well, a similar lifetime, and actually I'd expect a heat pump water heater to last longer than electric resistance, but adding a more expensive water heater, the life cycle cost changes. On the finance side, you see that now we're less than a conventional house by sealing it up, putting in a good ventilation system for fresh air, and less energy costs for hot water. And we can see that over here, that the water heater energy dropped, so that 18 gallons of water, hot water per year. We also see that there's been some impact because these hybrid water heaters cool the space they're in. There is a little bit more of a heating load on the house, but there's less of a cooling load. And these are taken into account. So the interaction between a heat pump water heater, as well as all appliances, are taken into account with how the house overall is operating. So so that was case 4 with the heat pump water heater. The third change we'll make to this conventional house on optimizing the insulation, I'll go to this level that already has it optimized, and we'll take a look at how much insulation that is, and we'll take a look at what these optimization arrows are doing. But with the addition of sealing the house, adding a ventilation system, and then adding a hybrid water heater, and then insulating to a thicker level, we're now at about 8,000 kilowatt hours per year, where we had been at about 12,000 for our initial case. And if we look at the, well, let's look at the envelope side. We're at about 13 inches of wall insulation, and we're at about 21 inches of roof insulation. Let's add an extra inch to the wall thickness, and I'll calculate that. Now, wall insulation costs about $5 per cubic foot based on our economic assumptions. We see that if I add another inch, my life cycle cost arrow now indicates any additional thickness. I'll see the life cycle cost go up. I did see an energy drop, and that's reflected over in this energy value, but overall it's saying we're thick enough economically. And if I do the same thing on the roof, and something that you'll find as you're trying to work your way toward optimal values, you'll find that there will be different combinations. This is a very complex multivariate problem. It might be that when you add a window of a certain size, or you add a change of efficiency to a certain appliance, you may see the optimal wall thickness change, where you had been optimal that now it isn't. Maybe it needs to be thicker, or maybe it needs to be thinner. And so that interplay is occurring within this as you move along. So that's what's happening on that basis. And if we look at the economics and we look at this kind of mini output screen, you can see that now each additional inch of insulation is going to cost me about $100 over 100 years. Not a lot, but the energy savings are getting pretty minor, especially as we talked about relative to what hot water costs are for every gallon per day that's used. Now let's get on to the fun part, and that's adding solar. We'll take case 5 and add enough solar in order to make that net zero. So I just went to that directly, and the only difference between case 5 and 6 is that now I put in 6,000 watts of solar. Now we needed about 7,800 kilowatt hours to be net zero. And just a rough rule of thumb, if you take the nominal wattage for a solar system, multiply that by about 0.2, for most of, say, mid-latitudes in the US, that will tell you the kilowatt hour of energy production. If you're more in the northern states or in Canada, that value might be more like 1. So a 6,000 watt system would produce maybe 6,000 kilowatt hours. And if you're more like, say, Phoenix or the southern US, that number might be about 1.4. So 6,000 watt system might give you a little over 8,000 kilowatt hours. And so when you see this number, just put in something near that number for the solar wattage. And then these costs, these are typical of about 6-7 years ago now. And so those costs are showing us that we would have about $355,000 life cycle costs. And if you remember, we had about $410,000 for the initial conventional case. And on the finance side of things, we'd have monthly payments because of that upfront cost for solar of about $1,600. And the solar added, we can see that detail here. We did assume the U.S. tax credit that may or may not be available in the near future. It's not going to matter so much in the future with the cost of solar, but basically this is showing us what our costs for the system are, our net costs, and then that is factored into the financing of the house. As we go back to the solar system, let's drop this down to where we are today, to about $3, and actually we're seeing $2.50 per watt systems going in for that level, so it's still not stopping. If I calculate that, I'm not going to see this energy change because it's the same size solar system, but I'm going to see this life cycle cost change, and I'm going to see what I have to finance change. So my life cycle cost dropped by about 25 grand over 100 years. That's pretty decent. My finance, I'm at around $1,560 versus the conventional house with lousy air quality. I now have a house with good air quality that uses a lot less energy, and it's going to cost me $30 more per month with the values in this. Let's go on to our last case, and we're going to add additional solar, so we're not only net zero, we're going to be able to power a car. In powering a car, in case 7, as we look at this, we're adding about 3,000 kilowatt hours. If we go over to the solar, I've bumped up from a 6,000 watt system to a 9,000 watt. Not too large, about 700 square feet based on these solar parameters. And these are decent parameters to use. You can change the tilt angle. This assumes south-facing solar panels. So adding 3,000 watts, as I mentioned for Equinox House, we added 2,000 watts, which gives us 8,000 miles of driving. And that's about our local electric driving currently. So we overproduce this. We look at the economics, and on the inputs, I've added a dollar benefit of 26 cents per kilowatt hour, and that's the value of the difference between 2 to 3 cents per mile for solar electric transportation and 12 to 13 cents per mile for gasoline powered transportation. And so this 26 cents is a savings in gas that's going into your pocket, but it's been converted to $1 per kilowatt hour. And so when we look at that, we find that that's roughly 12,000 miles of driving a year, typical of, say, about 30 miles of driving a day, and over the course of a year, 12,000 miles. For a 30 mile per gallon car, that would be about $700 of gasoline savings that are nice post-tax savings in your pocket. And over a course of 100 years, that would be about $70,000. You see the life cycle cost plummet because of adding this extra solar for your transportation. And when we go to the finance, because of that savings in the utility costs, we find that we're going to see a drop in our monthly payment. Now, I have $4.50 per kilowatt hour. I'm going to drop that down to $3, which is typical of today's cost, and I'm going to see a further drop. So now about $260,000 versus $410,000 for a conventional house. Because of these changes, sealing the house and putting in a good smart ventilation system, putting in a hybrid water heater, sealing, insulating the house to optimal levels, and then adding solar, and then getting an electric car when you're able to. And the net effect of that, where that conventional house had been about $1,500.30 per month, we're at about $1,515 per month. We're much less energy than what we have been in the conventional house. We're at an economical level of insulation, much lower life cycle costs, everything, I'm pinching myself the way the stars are aligning on these things, but everything is going in the right direction. I'm going to conclude here because I've gone much longer than I expected or had hoped, but there's a lot of material covered. I'm going to leave it to you to, these are just summaries of those cases that make it easier to see how to compare the impacts of these things on cost and energy for these different cases. As I mentioned, we will post both copies of these slides so you have those to thumb through at your convenience. And in addition, we will post the recorded version of this. So if I knocked you out and you're no longer conscious or you had to get somewhere else, you'll have that available. We appreciate your comments. Tell us how to improve this. Tell us what additional things that you would like covered. I'll try to get this more compacted into future talks. We'd like to explore different climates with you, different size of homes, different effects of occupants. We'd like your ideas on what topics that you would like us to cover should be, and we'll plan on putting this together into a package so that we address a lot of these topics as well as hopefully give you additional insight into how to use zeros. In the meantime, take care and stay in touch. Bye-bye.